characterization of compounds with expert Dr. S. Prabhakar Garu, Senior Principal Scientist, IICT Hyderabad. I hope everyone had acquired much knowledge from the previous sessions, and today we are blessed to have an eminent speaker to teach us spectrometry. We members of pharmacy bow our heads in respect to greet today's speaker, Dr. S. Prabhakar Garu, a man with an outstanding intellect, master in mass spectrometry, recipient of confidence, counselor, trainer, moreover, senior principal scientist, IICT Hyderabad. We're delighted to offer a rapturous welcome to Dr. S. Prabhakar Garu in this prestigious moment. I hope it's the most memorable day for Hindu College of Pharmacy. Many of them might have thought, could mass spectrometry be useful for us? There is no doubt in that. Yes, if you want to identify molecules in a mixture, detect impurities in a sample, study the protein content of a sample of cells, so on. In this regard, we need to acquire knowledge on mass spectrometry. In a nutshell, mass spectrometry accurately measures the mass of different molecules within a sample. Even large biomolecules like proteins are identifiable by mass. In mixed reprocessing samples, mass spectrometry is the only way to achieve high precision accountability measurements. So the main objective of today's session covers various advanced techniques of mass spectrometry in analysis of pharmaceutical and biological samples, recent developments and emerging directions in the area of electrospray ionization and mass spectrometry. Further, it will also highlight the application of mass spectrometry for drug development. So it could be helpful for method development of mass and as well as LC-MS for analysis of biological compounds. I wish all the participants a very pleasant, fruitful brainstorming experience in this event of learning. Now I request Ms. G. Indira Priyadarshini, Assistant Professor, Department of Pharmaceutical Analysis, to introduce about today's speaker. Over to Indira Priyadarshini.
Thank you very much, ma'am. I'm totally enthusiastic and waiting for the moment to introduce Dr. S. Prabhakar Garu, Principal Scientist, National Center of Mass Spectrometry to you all. Even though he don't need any introduction as he is so eminent to everyone. Dr. S. Prabhakar Garu was born on June 3, 1968. He completed his schooling in Nalgonda. Sir completed his BSc degree in Chemistry and Biology in 1989 and MSc degree in Organic Chemistry in 1992 from Osmania University, Hyderabad. Sir was awarded with PhD in Chemistry during 1997 on development of mass spectral techniques. For stereochemical problems in the area of organic mass spectrometry worked at CSIR IICT Hyderabad. Sir joined as a scientist at the National Center for Mass Spectrometry, CSIR, Institute of Chemical Technology, Hyderabad in 1998 and has been continuing research on the application of mass spectrometry in the area of organic chemistry and biology. Sir is currently working as a senior principal scientist at CSIR IICT Hyderabad. He had postdoctoral experience as research scientist from 2007 to 2009 at the Department of Chemistry, George Washington University, USA, and also as a research associate at Oxford Glycobiology Institute, University of Oxford, UK, from 2001 to 2003. Apart from this, Sir has visited around 29 different countries as a trainer, as a scientist, or what else. Let us know about his academic and research achievements. Sir has guided 8 PhD students, and of course, currently he is also guiding 8 PhD students in process. Sir also guided 10 MPharm or MSc dissertation students. He has published 145 research articles in the peer-reviewed international journals. Currently, Sir is working on metabolite profiling of body fluids, shotgun metabolomics, targeted metabolomics, metabolite markers in CKD and diabetes, protein identification, chiral discrimination, isolation, characterization and quantification of small molecules in biological fluids, drug stability and pharmacokinetics, chemical warfare agents and their degradation products, in situ identification of reaction intermediates. Sir has contributed to establish a dedicated and NABL accredited laboratory for the analysis of chemistry related to chemical weapons convention in environmental samples. There are several awards and honors, of course, there is no fun of it. Sir has received Eminent Mass Spectrometrist Award by ISMAS in 2013. He also awarded as Fellow of the Telangana Academy of Science in 2016. In 2014, he got CSIR Outstanding Performance Award. He also got awards like IICT Special Appreciation Award in 2008, CSIR IICT Gaurav Samman Award 2012, CSIR IICT Special Award for Skill Development Team in 2018, CSIR IICT Highest External Cash Flow Award Technical Services 2019, member of editorial board for the Rapid Communication in Mass Spectrometry, Journal of Chemistry and Science Journal of Medicine, and certified NABL SSR and GLP inspector. What not? Over the years, he obtained expertise in the characterization of structural elucidation of small and large biomolecules by using hyphenated mass spectrometric techniques. Right from inception, he has immense contributions to the Center for Analysis of Chemical Toxins. It is an NABL accredited laboratory for the off-site analysis of chemicals related to chemical weapons convention, and the team is regularly participating in official OPCW proficiency tests to retain prestigious international OPCW designation status to CACT. He has done a lot of contribution in R&D work in this area and developed libraries, CWC related degradation products and CWAs. So last but not least, Sir organized ASDC 2018 and 2019 on behalf of our CSIR IICT in almost 30 different countries in 2018 and 2019. It's Automotive Skill Development Council. Automotive Skill Development Council organized by our speaker today in 2018 and 2019 in almost 29 countries with various participants. So with this conclusion, I am introducing our speaker, today's speaker. Thank you for giving me this opportunity. Thank you. Over to Sunita ma'am.
With all my affable greetings, I cordially invite Dr. S. Prabhakar Garu to deliver the lecture. We are so thrilled to hear you, sir. Over to Dr. Prabhakar, sir. Sir.
Yeah, good morning, madam.
Please check the, welcome you, sir. Please check the background mirror image.
Yeah.
Now I am handing over the session to Dr. S. Prabhakar Garu. Please proceed, sir.
Is it okay, madam, now?
Yeah, it's good.
Yeah, so can I start, madam?
Yes, sir, please.
So, good morning, everyone. Thanks a lot to Professor Priyadarshini, madam, for such a long background of me. I'm a small man, so still had to achieve so many things. So, first of all, I thank Professor Sunita madam for giving me this opportunity through Hindu College of Pharmaceutical Analysis. So thank you. So it's my pleasure to be with you to discuss and share my knowledge in mass spectrometry. So I have been working
We are so glad to see you.
since last 20 years. So can I share my screen, madam?
Yes, sir. Please go ahead. Sir, try to connect it in new share.
Yeah, I think it's loading. It says you are
Yeah.
That's fine. Because maybe
Open, sir.
is it in full screen mode, madam?
Yeah. It's good, sir.
Okay. So first I will do disable participants annotations.
Okay.
So I think all set. May I go ahead?
Yes, sir.
So good morning, everyone. So I understand
Yeah, good morning, sir.
most of the people are from students and staff, faculty members. So keeping in mind of students, so though the title says so recent advances in mass spectrometry, but without touching basics, I felt it may not be good for the benefit of the student. So what I do is a few slides I touch upon basics and jump to the advanced techniques wherever if possible I'm going to insert and discuss with you. Okay.
Yes, sir.
So the overall this presentation includes the first thing is the basic principles of mass spectrometry, then the advances in mass for different molecules. So this is very important for student because those olden days people are looking for only volatile compounds, but now in pharmacy we need a non-volatile compound, proteins and peptides. So these advances are very important. So then madam already touched upon high resolution. So I will be covering high resolution, its importance, and hyphenated techniques. Like hyphenation means
Yes, sir.
you are combining two techniques together, like gas chromatography, mass spectrometry, liquid chromatography, mass spectrometry. So because these two are separated by an hyphen, it is called hyphenated technique. But nowadays they are putting a slash instead of hyphen, but abbreviation is hyphenated only. So then I will introduce to you, of course you know very well, importance of nitrogen rule and isotopic peaks in structural solutions. Then the tandem mass spectrometry, then interpretation of hard and soft ionizations. You will know with time what is hard ionization and what is soft ionization. And those who don't know much about the terminology in mass spectrometry, because in 90s things are changed. So we want to, even mass spectrometry people wanted to follow IUPAC rules. So please download this article. It will give you the terminology as per the IUPAC recommendations. So as an analyst, so any mass spectrometrist or any spectroscopist, those are called analysts. So there are only two questions for the analyst when they receive a sample. So what it is, inside at molecular level. And the next question would be, what is the quantity of the chemical present in the given sample. So for example, recent tragedy we have seen in LG Palmas in Vizag, and people definitely want, there are many samples were collected, even human samples, environmental samples, and people have been looking at what is in it and how much is there in the given samples. So it is very important to address these questions as an analyst, and mass spectrometry is possible for these two cases. So first of all, I would like to clarify because many people say any technique they use spectroscopy. like UV spectroscopy, visible spectroscopy, IR spectroscopy, NMR spectroscopy, but don't use for the same thing for mass spectrometry. Of course, there are some literature, people used mass spectroscopy very early, but later understanding the principles, what is the mass spectrometry, they changed scopy to metric. So only the difference you can see on the screen. Scopy means the final detection is through interaction of electromagnetic radiation, like UV visible. So there is absorption or emission of UV light or visible light. IR means radio frequency. I mean NMR is radio frequency. Yesterday you might have seen. So like that, there is nothing in mass spectrometry. You are not recording any electromagnetic radiation. So that's why the technique is called mass spectrometry. So I suggest all of you please use this word in future, specifically. The instrument is mass spectrometer, the technique is mass spectrometry, and the person like me who is working on mass spectrometry is called mass spectrometrist. Anyway, so if you see this one slide will give you the utility of mass spectrometer. First of all is the molecular weight. Of course, there is no other technique which can give the molecular weight. Okay, that's why the name itself is mass spectrometry. Mass means molecular weight. Yeah, as long as you are in Earth. Otherwise, the mass will be different in Moon. So I'm not going to touch that part. So the only thing is it is looking at the mass of the ions. That's what. And the second one is, can I analyze gas? Can I analyze liquid? Can I analyze solid? So I think all of them can be analyzed with the new techniques, which is possible in the present days. So even you can analyze gas samples also, but you need a gas collector, collecting vessels and those things. Okay. So if you have a pure sample, you can directly introduce it to the mass spectrometer. If you have a mixture, of course, any pharmaceutical analysis or any natural products, so you expect mixtures only. There can never be a single compound. So that's why you need to use chromatography technique before going to mass spectrometry. So as I told you earlier, it is called hyphenation with chromatography. So people think only GCMS, LCMS, but now commercial instruments are available with capillary electrophoresis mass spectrometry, HPTLC mass spectrometry, and whatnot. In future, it may be some other chromatography with mass spectrometry. It's only the imagination how technically you can combine these two techniques. So once you get the mass spectrum, so definitely it will give so much information in the given data. So for example, it will give you a number of carbon atoms and heteroatoms like sulfur, chlorine, bromine, silicon, like that, because of the isotopic patterns. So I'm going to cover some of them. So by looking at the spectrum, you can just quickly say, okay, this is present. And the recent one, because of the high resolution accurate mass values, so that means you are measuring the mass value till fourth decimal accurately. So that is possible because of high resolution instrument, and you are going to hear in this lecture also some of them. So because of measuring the high resolution, you can get the possible elemental composition. This is very crucial. Earlier, by getting molecular weight, you are searching in hundreds of possible molecules. But once you get elemental composition, the possible elemental composition, you are restricting to 10 molecules, then easy to characterize them. So this is very important and crucial for the mass spectrometry. But of course, all the facilities may not have a resolution, but you can use our services. And the next one is the structural illustration. Not only mass, not only elemental composition, you get like structure information. Like people, children, our children pay the puzzles. No, they have a picture and they make all bits and pieces, and finally they put together to get this the final actual picture. Like that, the molecule, if you fragment and you understand the fragment and put them back, then you can get structure information. So this is also crucial in mass spectrometry. and many times the structure which is not possible by other technique, it is giving up. I mean, it is giving, not giving up. So the last one is not only qualitative, it can do is highly sensitive technique. Now we are looking at parts per billion level, ppb level, nanogram per mm. So quantification is another one. So you can separate the molecules by chromatography, and you can also quantify by mass spectrometry. I think this is fantastic technique. There's no other applications this many, so that's why it's very popular. You name it in any field, the mass spectrometry being used. For example, you start with hydrogen or the carbon dioxide, oxygen level measurement. So for example, any earthquake is there, people are using mass spectrometer to detect whether the carbon dioxide is more in that area, so that people are breathing and carbon dioxide level will tell you there is someone who is breathing and oxygen levels are low. So like that, it is now beyond the small molecules. It is the mass spectrometry is applied for proteins, DNA molecules, whatnot, and it is sent to the Mars, and it was in Chandrayaan. Chandrayaan 2, it was not there, the XRO was sent, but Chandrayaan 1, the mass spectrometer was sent. So there is no limit for the mass spectrometer for the applications. So the only limitation is all the molecules are neutral. You have to ionize them either positive or negative. This is the only thing which is a must. And if you are unable to ionize a molecule, then sorry, you cannot use mass spectrometer. But with the techniques being developed to analyze all kind of molecules, there is nothing that you cannot analyze. Of course, there is like always 1%, some polymers may not be analyzed, but still development is going on. The other thing is that once the sample entered into the instrument, you cannot get back, but you can recover in HPLC, you can recover in NMR and all other techniques, but sample cannot be retrieved from mass spectrometry. But of course, you are just using a PPP level and you don't even need to recover at that level. So I think this has given the entire applications and use of the mass spectrometry. So this is my responsibility to, because this technique also brought Nobel laureates in abroad. You can see father of mass spectrometry, J.J. Thomson, and next Austin. All your periodic table is appeared because of the isotope detected by Austin, and then cyclotron, ion trap, and these two guys, Fenn and Tanaka. So I am fortunate to meet them in USA, and they also visited our center. Is glad to see them in our center. So these two actually developed electrospination and molding, because of which we are analyzing peptides, proteins, DNA, and so even 5 lakh molecular weight proteins have been analyzed now. Okay, so the technique goes around the molecular weight. So please, you should know how to calculate molecular weight. And of course, the sum of atomic weights in a molecule is the molecular weight. So you will be calculating atomic weight by number of protons and neutrons. But the only difference you have to observe is there is average mass and monoisotopic mass. So this is where students, for example, they do mistakes in calculating mass spectrometry, the actual molecular weight. So because the instrument is separating isotopes, you must use monoisotopic mass. Please don't use the average mass given in periodic table. Like every atom has the bottom is the average mass. And also please don't use the bottle molecular weight. This is also average mass. Okay. So many students I can see who joined recently, whenever they joined, they say after getting mass spectrum, sir, I got 1 unit higher, because they use the bottle molecular weight. Okay, so just use isotopic mass, and even Google will help you to calculate monoisotopic mass value. The average mass is only applicable to the molecular weight beyond 5,000 or 4,000. Okay, So those who are using peptides, bigger peptides and DNA protein, they only bother about average mass. All pharma people, so today I am pharma people. Okay. So as long as pharma is concerned, small molecules, peptides you use, and there is no necessary to use average mass, and our instruments will separate the isotopes. Okay. So this is the basic thing, and the isotopes have common nominal mass and monoisotopic mass is there here, and also the percentage. If you see most of the given in a table, the first isotope is high abundant. Okay, so that's why in a given mass spectrum, the bigger peak is always bigger, of course. Only the isotopes will be at the right side because all the most of the isotopes are lesser, like 1%, 5%, 0.1%, like that. You can see here. Okay, so most of the isotopes are at right hand side. Right. So that now finished the basic introduction. So when it comes to the basic principles, there are only 3 steps: production of ions, separation of ions,
Sir?
and addition of ions. Madam.
Please continue, sir. There is some interruption. Okay. Please.
Is it okay?
Yeah.
Yeah. So just think about only these 3 steps in mass spectrometry, and every step has advances. Okay. Forget about detector. Detector there are not so many, but production of ions is very crucial. That's where we are able to ionize small molecules, big molecules, everything. So I will be covering the advances in production of ions and separation of ions. Of course, whatever high resolution we are talking about, this is because of the analyzer, not because of the source and because of the detector. So I will be covering some of the analyzers which give the high resolution. Okay, so just remember, I will be starting with production of ions. I will spend time, then go to the analyzer. I will spend some time, come to detector, then I will give you the overall picture. Okay, so this is the thing. Any molecule, it is ionized in the source, and in the analyzer it will separate and detector. And first it gives the time versus abundance plot. Then you calibrate the instrument, and you get mass versus abundance. Okay. I will not spend time on calculation, but maybe you can check later, or I can give you at the end about calculation. So if you look at the, just I want to give some pictures so that you can visualize where exactly mass spectrometry is being used. The first one, which very big one, this is my favorite equipment which I worked on my PhD time. It is occupying a full hall, a size, that much size, big size. So this is because of the magnetic sector instrument. The analyzer is magnet. And later on, the magnet was removed and we have a quarter pole instrument where you can see very small.
Sir, there is interruption. Prabhakar, sir.
That is okay?
Yeah, now it's audible.
Yeah, please do that because I don't know. So please stop me when
Yeah.
there is a problem. Okay, so
Okay.
you see, this is very latest equipment, like a HPLC PGA detector. You have a mass spectrometer on the top. Such a small mass spectrometer was developed, and you can see the mass spectrometer in the fuming cupboard, organic synthetic people, and you can see mass spectrometer in the space. I told you, it was sent to the Mars, whether water is there or not. They want. So like this, you can see developments in mass spectrometry in analyzers, sources, and whatnot. Anyway, so first thing, as I told you, you have to generate ions. So there are only 2 types to generate ions. The first one is you are playing with electrons. This is the classical example. Up to masters, you see this technique. So this is called electron ionization, and this is also called hard ionization. So I'll tell you why it is called hard ionization. So the only thing is, if you remove one electron from a molecule or from an atom in a molecule, which is loosely bound, it's like a first ionization potential, what we call, right? So if you remove one electron, you get M plus dot. So this is called odd electron ion because there is a free radical. And if you add one electron, negative ion. But negative ions are very less abundant, maybe 1:1000. So that's why electron ionization mostly people use positive ion. Okay. So this is hard ionization. And the other technique is the addition of ion to the neutral molecule. So this is called soft ionization, where you are adding a proton or a sodium or a potassium or ammonia. So these are all ions. One, sorry, I'm a webinar. Sorry about that. You are adding a proton to the neutral molecule to get a protonated molecule or sodiated molecule. That's all. You can use any technique, but this is the positive ionization. In the case of negative ionization, people use chloride or sulfate. Chloride, where from it come? If you use ammonium chloride as a buffer, it will come chloride. So like that, you can add also sulfate ion to get sulfate ion. Or you can remove a proton to get a negative ion. Okay, but again, negative ion is lessly used more than positive, right? So these are all in GCMS you use electron ionization, chemical ionization. In LCMS you use these three techniques. I will touch one slide each later, but these are the ions formed in positive ion and negative ion. Okay, so all participants they will be getting a PDF version of this one. So just listen, and madam will share you the PDF version of presentation. Okay, then you might have a doubt how to choose a positive ion mode operation or negative ion mode. So usually positive ion for any basic compound or any esters, carbonyls. So these are all positive. They are very sensitive and positive. Okay. Negative like acid, nitro group, alcohol, halogen. So by looking at the structure itself, we can decide whether it can come in positive ion or negative ion. Okay. So this is our suggestion to the student just to choose because sometimes people, if you don't get in positive, obviously they record in negative. But this will give you some idea. So next, this is a same example only. So this is a basic compound you can see. So basic compound easily protonate and give you the positive ion. That's why the basic compound, the positive ion mode detection is better. So for example, negative ion, for example, acid compound, it will remove proton easily. It will form a negative ion. So that's why negative ion mode is better for acids. Okay, so mostly people use GCMS and LCMS. Okay, so GCMS, as you know, it is for volatile compounds, and LCMS is for non-volatile compounds and thermally level compounds. So GCMS will give you like a chromatogram like this. So these are the individual peak. So this many compounds were there in a mixture. They separated in gas chromatography and detected later in the mass spectrometer. So in GCMS, you have electron ionization source. So you have molecular ion and you have fragment ions. So that's why it is called hard ionization. And next slide also will come. Whereas in the LCMS, because electrospray ionization or APCA or APPI, you get only M plus H ion mostly. Fragments for a best ionization, best conditions, you must get only one ion, usually protonated or sodiated, whatever. So there is no fragmentation possible in electrospray ionization unless you increase the voltage and you don't tune well. Otherwise, it's supposed to give at an optimum condition. It's supposed to give single peak. Okay. So in chromatography, you know the chromatography principles. I am not going to go in details. The mobile phase and the stationary phase. The stationary phase will try to hold the molecule, whereas the mobile phase will try to push the molecule through the stationary phase. So this is the artificial, like an artist model to write. So let's just see the electron ionization mode in GCMS. So this is the source, and these are the electron beam. I am not going to detail. Madam already might have covered. The only thing is the spectrum. What you get, you get molecular ion and or fragment ions. It is equivalent to a fingerprint of molecule, like our Aadhaar. Okay, like Aadhaar print, you have a fingerprint of molecule. So simply you search in the library, you get identification. You don't have to interpret anything. As long as the molecule is known, it is present in the database. If not, of course, you have to interpret. Okay. Then why it is called hot ionization? So I told you electron ionization. First, it removes one electron. It is equivalent to first ionization potential of the molecule.
So again,
Yeah, is it back, madam?
yeah, okay.
The first ionization potential normally it will be 15 to 20 electron volts, whereas we apply 70 electron volts, which is more than required. Actually, this is our purposefully we are giving. It is sensitivity is very high at 70 eV. Not only that, molecule is breaking. We want fragment ions also to get the structure. So that's why this is called hot ionization. It is ionizing and breaking the molecule. Okay. So this fragmentation we'll see at the end. So this is the spectrum where the base peak is the highly abundant peak and extreme right peak is the molecular ion. You get isotopes. In every peak, it should have isotopes. Okay. If there are no isotopes in the mass spectrum, please don't consider it for interpretation. The recording is something wrong. Okay. You must get isotopes in a spectrum. And never think always base peak is molecular ion. Okay, and all this base peak fragment ions, it comes only in the electron ionization. But if you look at LCMS spectrum, there is no question of base peak, so it's just one peak you get from the molecule. Right, so then I just touch LCMS because this is more important, and there is a Nobel Prize winner for this technique for the invention of electrospionage. So, as you know, there is a in HPLC, you know, normal phase and reverse phase, and I'm not going to be detailed, but you know how people start with non-polar to polar and polar to non-polar in two different cases. Okay. Uh, so the advantage is in HPLC and UPLC. This you must know because UPLC is a new technique where you use low particle size column. The back pressure is very high, so the system operates at very high pressure, and it requires only low flow rates of mobile phase and fast elution. So because of this, now almost all industry people they stopped HPLC. Now people are using only UPLC. Only thing is maintenance problem because it is working at high pressure and low flow rate, but it does wonders, and HPLC can analyze per day only 20-30, whereas here hundreds of samples can be analyzed by UPLC. Okay, so you must know the details of UPLC. But my concern is what was the problem in connecting HPLC to the mass spectrometer? So as I told you, mass spectrometer works under vacuum because you are generating unstable ions which are not stable in the environment. Whereas HPLC is a high pressure liquid is coming, and the liquid, if converted to the gas, it will be thousands times higher. So the mass spectrometer cannot handle coupling of HPLC to mass spectrometer. That was the situation in 1990s. Okay, there is one artist. He draw this picture. You can see the parrot is the one which is mass spectrometer. It works in only in the gas phase, whereas the HPLC is a fish. It will work only in a liquid phase. So now you want to couple these two, which is impossible those days. Then scientists worked a lot to get a parrotfish, so that now it is possible because of this tail fish. Okay, so that is our electrospray now. Okay, so let us see. So now two teams work together, HPLC team and mass spectrometry team. Of course, there are many problems when they are connecting, but finally it's a teamwork and people succeeded. Now we have a correct track in LCMS. So let us see how it was possible. Earlier, people thought mass spectrometer event source is under vacuum. Now, LCMS, the source is not under vacuum. Because of that only, it is possible to connect HPLC to mass spectrometer. That means this is atmospheric pressure ionization. That means as long as you are ionizing atmospheric pressure, no issue, immediately it is sent to the analyzer, which is under vacuum, it is stable. Okay. So if you see electrospray ionization, so it is very simple. There is a needle, you apply high voltage like 3 to 5 kilovolts. So once you apply the high voltage, you can see in the inserted one, there is a spray of the liquid. Okay. So that is why the name itself will tell you electrospray. Many people wrongly use as electron spray. You are not spraying electrons here. Electron ionization is different. Electrospray ionization means your electric field you are applying to get the spray. Okay, you are applying high voltage. Okay, so many students will confuse between electron ionization and electrospray ionization. Okay, please remember you are applying electric field. Okay, so if you apply positive field, it is positive ions. If you apply negative field, it is negative ion. That's all. Easily to get positive ion, negative ion in this case. And nowadays instruments have come. One scan positive ion mode, one scan negative ion mode. You don't have to even run 2 times. Okay, that much advances are there now. Okay. So anyway, Sunita madam already might have covered you how the electrospray works and how droplets are formed. Now we are worried about droplets, right? So we also have our droplets for coronavirus, but these droplets are safe and these are electrically charged droplets. And because of nitrogen, it will evaporate and they get the gas phase ions. So I leave it at this stage. Go to the next one. So the technique is simply applying high voltage. Okay. Then people thought, okay, let us do for so many other things. This is called paper spray. Actually, paper is not very dry, right? So, but if you apply solvent on the paper, it will be wet. So once it is wet, you can apply high voltage. So you can see here, you load the sample on the trigonal this one because you need a sharp end. So once you apply the sample and once you apply your solution, water, methanol, whatever, it is wet. Now you apply high voltage. Immediately it will spray, you get the ions and goes to the analyzer detected. Fantastic, right? So I don't know how many people know about it, but this has been used in currency notes and in blood samples, urine samples, and even to identify the fake checks, because fake check they use a wrong ink So you can put a drop of solvent in the wrong ink, put it on the paper, load it, and just you get the spectrum. Okay, the molecular weight of the ink pen, what is the chemical used, it will come there. So this is the one advances in they extended again electrospray. So you will also surprise.
Sir, sir, we are unable to hear. Prabhakar, sir. Yes, yes, we are informing to the speaker. Sir, there is a interruption. We are unable
Yeah,
to
now
hear
it must be
voice.
okay.
Now it's connecting. Sir.
Yeah, it's okay now.
Yeah.
Yeah. So this is another one called leaf spray. Okay. Here you don't have to wet it. Leaf is already wet. You have I don't know how much, 70% water in every cell. So you sometimes if you want you can load methanol or something to dissolve the compounds, but you apply the voltage, and this has been used for many natural compounds analysis. You can see tulasi is analyzed, sanctum and whatnot. This is what we use, kalabanda we say. Yeah. So it has been applied to many natural compounds directly. You don't have to extract anything. So in IIT Chennai, one professor is using this one. So, but it is possible. This is your imagination. Okay. So this is about extension of electrospray ionization. We have another technique in LCMS. So here uh, the probe has heating. There is no electric field here. The vapor comes. Now the vapor is the gas phase. So you need a needle at high voltage to ionize. So this is for a thermal unstable compound. It is equivalent to chemical ionization in CI, GCCI. Okay. So this is the new source which is coming up, where both you can get electrospray and APCI. So you don't have to run twice, one electrospray, one APCI. So you see this is electrospray probe, and if something is not ionized, you keep a APCI needle here, whatever neutral it is ionized and sent back. Okay, so this is called multi-mode source in of course one company says multi-mode, but many names were there, but you can get this technique in recent technology to, if the sample is less and one run, if you want to have both, you can have. So the other technique is APPA, atmospheric pressure photoionization. So usually the name itself will tell you what it is. Here is the photo. Photo means photons. So then it's like a APCA probe only. Instead of corona needle, you use a source of photons, 10 electron photons. So it's just the same. Photons will ionize. Here you get molecular ion or M plus H. Okay. So this is also soft ionization. So at the end, you have a big interface between HPLC and GC with mass spectrometer. If GC, if it is volatile, you can have GC EICA, and if it is LC, you can have APCA, electrospray, and a new technique is APPI. Okay, so but thing is, when it comes to the mass spectrometer, you are looking at volatile buffer, volatile nature of the molecule like that. So that's why every HPLC mobile phase you cannot keep to mass spectrometer. Okay, so there are some restrictions when it comes to LCMS. All HPLC methods you cannot apply to LCMS. You have to look at the buffers what we are using. Okay, so normally mass spectrometer does not like buffers at all. like no phosphate buffer, no other non-volatile buffers. You can use volatile buffers like ammonium acetate, formic acid, acetic acid. Okay? It has to be a volatile buffer. What happens if it is non-volatile? So it will not, when you are spraying, it will be there in the source only. It will block your mass spectrometry. So the ions generated depends on your buffer used. Okay, this is also very important. For example, if you are using ammonium acetate buffer, so definitely you get ammonium adductor M plus NH4 plus. That means molecule plus 18. Okay, so like that, the buffers, everything you should remember. That will decide what is the ion you are getting. Okay, in negative ion mode, for example, if you use a ammonium chloride buffer, you get chlorine addition M plus Cl minus. So don't surprise that where from I got chloride. Chlorine is from the solvent. Your molecule doesn't have a chlorine. Okay? But if your molecule has a chlorine, then it will add up and give a isotopic pattern accordingly. Okay? So usually if you really want to adjust the pH, because if the pH is essential for you, you adjust your pH with acetic acid, formic acid, at the end trifluoroacetic acid. Okay, these are all okay. If you want basic pH, you can use ammonium acetate, ammonium formate, not others. Okay. Sometimes you can use ion pair reagents. You can use pentafluorocarbonate or dibutylamine, trimethylamine. These are volatile, so you can use. If possible, you can avoid. But if it is essential, sometimes quickly you can use ion pair and clean up your lines and source and immediate. Because whatever you analyze later, everything comes same. Okay. So these are the, but never ever use dimethyl sulfoxide, dimethyl formamide, phosphate, dichloromethane as a solvent, chloroform as a solvent, because these two will interfere with your ionization. They are non-polar, they will not give you a proton to the molecule. So don't use dichloromethane chloroform. But what happens if your sample is only soluble in dichloromethane or chloroform? So you have to use mixed solvent. Use dichloromethane and methanol, so that methanol will help you in ionization. Okay, so these are the precautions you have to take when you plan your LCMS. Don't say I have not got anything in LCMS. If you don't plan LCMS correctly, you don't get ionization and other things. Okay, so these are the volatile buffers for your information. I think more than enough those are available in the literature. So I think now I finished GCMS and LCMS. In the ionization source, there is one more left, which is Maldi, which brought again a Nobel laureate in this technique, Kochi Tanaka. Of course, he accidentally found, but he himself don't accept how I invented this Maldi. Okay, so Maldi is nothing but you use a solid matrix, mix your sample in a solvent, matrix in a solvent in 1:1000, and load it on the target and remove the solvent naturally, or you can blow air, and after that it will co-crystallize in the target. So now you have to irradiate with laser. Okay, this is where people will confuse. I'll tell you later. Now you are using UV laser or IR laser for ionization. Okay, so your laser power is absorbed by the matrix, not by the compound. That's why the matrix is 1000 times higher than the analyte. It takes the energy and excites. That energy is transferred to the your molecule. During the process, it will protonate or it will become molecular ion. So one spectrum is given here. It is M plus H. If it is a protein, you get W charge, W charge. Okay. Now the laser is electromagnetic radiation. Can you say mass spectroscopy now? No, because you are using in ionization only. Once the ion is formed, analyzing in the analyzer, detection is same. You are detecting current, not the laser electromagnetic radiation. That's why even MALDI is not, because of MALDI, it is not mass spectroscopy. Okay, so MALDI normally uses time of flight analyzer. So here the time of flight analyzer is very simple, like a running race, what we call. Okay, so if the running race is 100 meters, if they are champions, you cannot differentiate them, right? So that's why we have in running race 500 meters or 1000 meters, because small running distance anybody can reach. So like that, in a time of flight also, they have a reflector on top where you can use the path up, double the path or triple the path, so that you can separate these little rats which are coming almost same time in the linear. In the reflectron, you can see this blue color is coming faster. So that means it is helping you in the separation of ions which are closely coming. So this is the high resolution which I talking. Okay, so because MALDI has come, I am just giving 2-3 examples here. Then I will jump to other thing. MALDI is fantastic for the microbial identification. So now US FDA approved method is there. Just take your microbial sample, load it on the target, mix with matrix. What happens? The bacterial cell opens up. It gives you soluble peptides, proteins, lipids, and you are not going to identify what it is. It is like your Aadhaar card profile type. That's all. So you can see here, E. coli gives these peaks, lactis will give this peaks. That's all. You are comparing only the spectrum and identifying. So this is the library is available for more than hundreds of microorganisms, and people are applying now. But don't try for coronavirus. It is not applicable now, because that is different. Okay, this is for safe bacteria, not for the virus. So this is fungi. MALDI also use fungal sample, same principle. And other thing is the imaging. I think I don't know how many people can understand what is an imaging. Image is like in a given sample, how the target molecule is distributed. Okay, if you give a drug to the molecule, any rat or something, you need to know whether the drug is gone to liver, drug is gone to brain, or drug is gone to whatever part you want to go. So this image will tell you whether the drug is entered, because we are monitoring the drug molecule ion. Okay, you have to mix 10 micron slice, put it in the MALDI and apply matrix, and you are applying matrix like a small dot, and you will be recording the spectrum there only. Okay, so you will record multiple mass spectra. If it is cited here, you get the mass spectrum. If the molecule is there, you will get ion. If the molecule is not there, you don't get ion. Finally, you get an image here. Okay, so this is one image you can see, rat brain image. This is I think one of the protein they analyze, but you can do any small molecule also. So you can see only this area, that protein is there. It's very beautiful. So you can see here it blue. It is tested by me. So I have put on the target IICT. Okay. Purposefully I used different color pens. The second eye is not very intense, because that is a weak pen. Okay, so this is how you can get an image of a chemical. So here I analyze the molecule which is there in the pan. Okay, so this is a very beautiful advanced technique, the imaging mass spectrometry, and very important for drugs and pharmaceutical drug development, and in that case. Okay, so what not? You have TLC modeling, HPTLC, you can combine with the mass spectrometer. This is very advanced technique. You have a HPTLC with electrospination. Okay, this is all imagination. This is electrophoresis with mass spectrometer. Okay, so all are coming. Only thing is you have to use, and it is maybe expensive, maybe 1 crore to 5 crores. Okay, so these are the other ionization techniques. I think we can go on like this. There is no end to the advances.
Yeah.
Okay, so this is called DAISY and this is called DART technique. DART is available in Lucknow. Okay, now recently there is a problem with the instrument, but you can directly put anything in front of the mass spectrometer. You spray like a spray. You can spray the solvent and you get the spectrum. Okay, so this is fantastic technique, and I also fortunately involved in a technique called laser ablation electrospionization, where I can keep the active cells in front of the mass spectrometer. I'm the first one to keep the infected cells in front of the mass spectrometer, and to identify whether infected or not infected. Okay, so you can follow my publications. So this technique which I developed, it was one of the top 10 innovations in 2011 at Washington University. Okay, now it is commercialized and people can use. But of course, the laser here they have to use IR laser, which is difficult and expensive. So this technique has to develop in India, but I don't know. It may come in future. So this is another application of modeling. You can see the doctor is operating. Okay, so there is a one sampling in the beginning of the knife. When it is about to cut to the tissue, it will collect the tissue volatile samples and send it to the mass spectrometer immediately. So here this knife is helping the doctor whether he is cutting the cancerous tissue or not. Okay, so this is a live application. It is called intelligent knife, which is developed in London, Imperial College London. And I think, of course, there are many developments yet to come, but this is one of the applications in life science. And there is a Professor Cooks is there, and he actually applied this technique for identifying the TB patients. He will put a tube in the ear and he will identify the sample will go to the next room. This sample will go to a tube and detect there, and we will know whether it is a TB patient or not. So like that, mass spectrometry is being applied for medical science also. So I think there is no limit. Environmental, you know the plants, everything, but this is the medical science applications. So this will entail the advances in ionization handling with the different samples. Okay. So now I am coming to the analyzer part. Okay. The analyzer means you ionize now. You have to separate the ions. So this is well known. Dr. Sunita madam already explained you how the magnet works. So any ion which is in the magnetic field, it will take a circular path and you have to scan the magnetic field up to bottom and you get a nice so I'm not going to spend time on this. And there is another analyzer, the quadrupole analyzer. where the four rods will be there, opposite rods are connected, and opposite rods are applied AC and DC voltage. Okay, so at a particular AC DC voltage, only one molecule, one ion can resonate and pass through. Okay, in this case, only the red ion is resonating and passing through. All others are different frequency and they will die there only. So that means if you sweep this voltage from low to high voltage, one of the other it will go to the detector. But at a given one, only one ion is going, only one ion. That's why this is called mass filter. Okay? If you want only 100 mass, only you can put 100, only 100 will go there. So you can control your passing. Okay, like your police in a corona case, if you have a pass, then only you are you can go through the that barricade. So like that here also, you can control the ions entering into the detector. Okay, so this is again it has come. Sorry, I think twice it has come, but here the reflectron and this is a part of separation technique in high resolution. ఉన్నాను నేను వేరే దాంట్లో ఉన్నాను వేరే ఉన్నారు సారీ yeah so sorry about it. So I think these two analyzers, high resolution analyzer, and I'll give you some more later high resolution one. So this is very important for elemental composition. I told you it will give you the mass value up to 4th decimal. So at the end now you ionized, you separated, and the detector. Detector is very simple. Any ion which is detector is nothing but a metal plate. Any ion which is touching the metal plate, what happens? Metal plate is rich of electrons. Now your positive ion is one electron less, right? So it will take that one electron and neutralize. Once it is neutralized, it will go to vacuum pump. But this one electron transfer causes some current in the detector, and that current you are measuring. Okay, but only thing is the current generated in a small ion is very low. You have to increase the current. You have to extrapolate the current this one to get the measurable current. That's why detectors are called electron multipliers. Okay, if one electron is generated, at the end 10 to the power of 6 electrons are generated in the electron multiplier. So that's why this is measurable current, you can measure. So like that there is no choice in detector, electron multiplier, photon multiplier. Micro channel plate is the latest one, where each channel is one electron multiplier. So this is used for time of flight analyzers. Okay, so these are the advantages in the detectors. Okay, right now this is very important slide. You heard about sources, you heard about analyzer, and you know the detectors available in the market. It's like your pizza, right? When you order pizza, whatever you want you can select. So here also you can select one ionization source, one analyzer, one detector. It is your choice. Now the commercial, all types of instruments are available in commercial, and it is your choice and your money. Okay, so if you have a, for example, a quadrupole time of flight analyzer, it is called QTOF, and if you have a MALDI with the time of flight, it is called MALDI TOF. So even name itself will tell you what it is. Okay, so it finishes the overall the principles of mass spectrometry. So now I will touch upon the high resolution, which I am telling. So high resolution is simply how well you resolve two ions which are very close. Okay, With low resolution, you can separate only 100 and 101, not 100.1. So we are looking 100.1 also to be separated. That's why we need high resolution. And I don't know how many people know the spectrum is line spectrum, or like other NMR, IR, UV, you get a Gaussian peak. Many people think mass spectrum is a line spectrum.
Line spectrum.
No, actually, the detected, it all detected. Actual peak is a this continuous spectrum. We say this is a Gaussian set peaks only. The computer only makes it centroid and will give you the centroid spectrum. Okay, we should not teach. We get only line spectrum. Okay, we will get continuous spectrum. Only problem here is the continuous spectrum. It will take more data, the data points. Okay, if you choose LCMS, your continuous spectrum, it will complete your 10 GB or 20 GB. It will take. So that's why they give it to the detector. Sir, please convert to the line spectrum so that I will get less data points. Okay, so because it's Gaussian peak, there is a high resolution. Okay, the peak width is very high, then you cannot separate two peaks. So the high resolution, what it does is the peak width is narrowed down. That's all. So that is high resolution. So you can see in the next slide. Okay, before so these are low resolution analyzer. These are the high resolution analyzer. So we have FTMS. I think FTMS is not manufactured nowadays. Very difficult to manage. There was only one FTMS long back in 80s, 90s in IISc Bangalore, but later it was dropped down. People are also not making FTMS. So what we have now is arbitrary, time of flight, magnetic sector only for specific purpose like dioxins and all. But if you are living with only arbitrary or time of flight instruments, that is it. Okay, so this is a magnetic sector instrument. I already showed you. In 1993, ISCT has 80,000 resolution magnetic sector instrument. So this was the, I don't know, first one in India, maybe, and we used to get samples all over the country to the institute for high resolution analysis, including IISc Bangalore, whatnot. Okay, so I am fortunate to work on this instrument. But now people are shifted. So left side, these two now not there, and right side you have a QTOF instrument where your time of flight is visible here, but there are other instruments, time of flight is inside, it is not visible, but you don't think that flight tube is not there. Some instruments are like this, some instruments are like this. So the other instrument which is called arbiter, this is a new technique, very high resolution, 1 lakh. You can get even 2 lakhs resolution in this instrument. QTOF, you can go 40,000 resolution. So it all depends on how much resolution you require. You have to buy that particular equipment. So for small molecules, you can use QTOF. If you want more high resolution, you can go to arbiter. So we have these two equipment. So what happens in high resolution? You are measuring accurate mass. Accurate mass is experimental mass determined till 4th decimal. Okay, don't confuse with exact mass. Exact mass is a calculated mass. You are not measured by mass spectrometer. It is a theoretical mass. Okay, don't ever say I record HR high resolution mass spectrum. The exact mass value is this one. No, you have to use accurate mass. It is an experimental mass. So when you write your manuscripts, you have to use carefully. So anyway, you can ask our Google Mata to give you all exact mass values, it is available. You don't have to bother, and you type in your formula, it will give you the exact mass value of your compound. Only you have to check it with the accurate mass. Okay, I just give you simple resolution, how the resolution differentiate, how the resolution will separate small molecules. So you can see here, there are three molecules we are analyzing. One is carbon monoxide, nitrogen, ethylene. If you use a routine mass, all are 28 mass, nominal mass, you get single peak. At high resolution, for example, at the resolution of 2300, now my ethylene is separated, but not carbon monoxide.
Sir, sir, there is interruption. Prabhakar, sir. Sir, we are unable to hear you. Sir,
Is it okay now?
now it's connected, yeah.
Yeah. So if I
Sir, again, it's breaking.
yeah, I think now it's fine.
Yeah, go ahead, sir.
Sir, there is other webinar going on in the institute, our own institute.
Okay.
This is at 5000 resolution. You can see these two peaks are nicely separated. At 1 lakh resolution, the carbon monoxide, nitrogen, which is close here, these are like miles away. Okay, this is 1 lakh resolution. Even if you have another 5 molecules here, it can separate. So this is the beauty of high resolution. Even though you have mixed ions at the very close molecular weight, you can detect. So for example, it is my own spectrum, you can see. So I am analyzing a biological molecule. The molecular weight is 203. Okay. The low resolution, you think it is only glucose. Glucose sodium addictive is 203. But the same one, if you put in a high resolution, there are two peaks, 203.0558 and 0.2. So these two are different molecules. One is Fermi, otherwise glucose. So like that, the applications are very huge when you get a high resolution mass spec. Okay, you can many see, you can hear choline and GABA separated, here lysine and glutamine separated. Okay, so these are already covered: magnetic sector resolution, time of flight resolution, arbitrage, FTMS. So I would like to have arbitrage, if not the time of flight. Okay, so now we finished the major part. So if you see here, if you are using only gas chromatography or liquid chromatography, it is called a two-dimension. That means you are getting the retention time and you are also getting intensity. Okay, so it is a 2D. So when it comes to mass spectrometer, you are getting retention time, you are getting the intensity, and also the mass spectrum of the peak, right? So it is a 3-dimension, 3D. So now, as I told you, in LCMS, you get only single peak. Single peak, you cannot get structure information. So there is another technique called MSMS, where you select that single peak and you break it by bombarding with energy and gas. So that is MSMS spectrum. That is the 4th dimension. Okay, and it is 4D, right? So in like mobile, our mobiles now we are in 5D. I don't know. So like this in chromatography also we have now 5D also, where image, I told you, image mass spectrum, that is another 5 dimension. So like that, there is no end with the mass spectrometer. That many information you are getting in a single run. So now I just give you the introduction to the MSMS. So tandem mass spectrometry. MSMS is nothing but you are using more than one analyzer. That's all. Your source is same, your analyzer is same. You have more than one analyzer. That's all. Okay. That's why it is called MSMS. Doesn't mean that two mass spectrometers are attached. No. Single source, single analyzer. So actually in MSMS, there are different scan modes. I don't know whether you heard in NMR like NOSI, COSI, C13, F19, like that, HMQC, like that. In mass spectrometry also, even in MSMS, you have product RAN, Verekas RAN, neutral loss, neutral gain, multiple reaction monitoring. These are all different scans. Okay, so you may not understand all these, but what we normally use a product and scan, where you select one ion, you break it, the fragments which are coming, that you are getting the spectrum, that is called product and scan. Okay, you know, earlier terminology, it is called dot ions. But after IUPAC nomenclature, people fighting why daughter, why not son? Okay, can I have son ions also, right? So like that, they change to product ion. Similarly, precursor ion, parent can be mother or father. Okay, so then they put a precursor ion scan. Like that, terminology is changed. You remember the actual MSMS is a dot ion. And quantification, you use multiple reaction monitoring. Okay, I'm not going to explain. It will take 1 hour to know what is what. Right. This is just one example. One drug. You can clearly see HPLC will give you a very nice single peak, and positive ion electrospionation. It gave you M plus H, very good spectrum. Okay, but you got HRMS, you got elemental composition, you got isotopes, but structure information you know you don't have. Then you break it, you select break MSMS. So this is MSMS spectrum, where this is your parent and this is your product tanks. So based on this product tank, you see 256, 150. This is structure. The 256 is nothing but it is breaking this part. Okay, it is known piperazine will break like this C2H5N to give this ion. Okay, so the other part is this one 150. This 150 will tell you this cleavage, sulfur cleavage. Okay, and it will combine here. Okay. So like that, structural elucidation you can get where you, but of course you have to interpret the data, and there are some rules to interpret. I will let you know later. So this is MSMS. Okay. So now I think I finished all the basic principles, advances in mass spectrometry, high resolution, MSMS. Okay. Now let's go to interpretation part. So I already told you we need to get molecular weight information at the first. Okay. So how do you get molecular weight information? I told you you don't know which ion you got. Okay. In that way, electron ionization is better. It gives molecular ion directly. You don't have to do anything. Okay. But to other techniques, you must know how the ion is formed. Then only you can get molecular. Okay. If it is M plus H, it is M plus 1. 1 unit added. You have to remove 1 unit to get the molecular weight. If it is ammonia added, you remove 18 and you get molecular weight. Like that. If it is sodium added, remove 23, you get molecular weight. Yeah. Is it any break?
Continue, sir.
So I'll take one water break.
Okay, sir.
So if it is a potassium adduct, you remove 39. You get this information. But
Sir,
yeah.
sir, M plus sodium, M plus 23 you mentioned. Why, sir?
Plus sodium, 23 it will add.
Why, sir?
You have to remove 23 to get molecular weight of the compound. So normally, if you put in HPLC, you don't see sodium and potassium. Normally you get M plus H. But sometimes if the buffer has water, the water may contain a little bit sodium, traces of sodium, then it will give you sodium adduct. Okay, so if it is in acidic medium, your buffer is in acidic medium, then there is no question of sodium. So you need to be some idea what kind of ion it can form, then only you get molecular information. So very crucial. You should know what is the mass spectra you are looking at. Okay, then possible ions, everything is given here. You can get molecular weight. So once you get molecular weight, then you can go to nitrogen rule. But don't apply nitrogen rule to every ion. Okay, not protein. It should apply to only molecular weight or molecular ion. If the molecular weight is even mass, so there are either no nitrogens or even nitrogen. If the molecular weight is odd mass, then there are odd number of nitrogens, like 1 nitrogen, 3 nitrogen, 5 nitrogen. So this is well known masters time you can get. The only difference because why nitrogen rule has come, because the atomic weight and valency in all other cases, atomic weight, valency, either both are even or both are odd. Whereas nitrogen, atomic weight is even, valence is odd. So that's why this nitrogen rule has come. Okay. So simply you can see in this example, nitrogen rule you can apply, and if there are no nitrogen, even number, one nitrogen, odd number, easy. So once you get an unknown compound, first thing is look at the molecular weight, look at the nitrogen group. Then you can avoid whether nitrogen is there or not, even number, odd number. So already you got some information, this nitrogen group. The second information is the isotopes. Okay. So I hope you are already taught to them, but isotopes, the first one, second one, M plus 1, M plus 2. This is electron ionization data, but even M plus H you will get same M plus 1, M plus 2. Okay. So this M plus 1 will give you number of carbons information. The M plus 2 will give you heteroatoms like oxygen, sulfur, and fluorine, chlorine, silicon sometimes M plus 2. Okay. So now if you see the table, you can understand. Okay. So what is the isotope which is contributing to M plus 1, M plus 2, you can see. Okay. Here sulfur, it is M plus 2, it is contributing. So chlorine also M plus 2, bromine also M plus 2. But if we have multiple numbers, it will have M plus 4, M plus 6 also. Okay, this is one example. If you have 10 carbons, your molecule, your M plus 1 is 11%. If you have 50 carbons in your molecule, you have 55% of M plus 1. One example is my favorite molecule. Many times we analyzed this buccal C60. So C60 means 60 carbons. So obviously you have 66% carbons. If you have 100 carbons like protein, peptide, the M plus 1 is very high than C12. Okay. So those who are analyzing protein, peptides, you must know what is C12, what is C13. Okay, then they confuse this is molecular weight or this is molecular weight. Okay, so for pharmaceuticals, don't worry, you will have, you are here only, your C12 peak only very high, so then there is no issue. But proteins and others, you have to look at first. So this is simple example how chlorine is employed. 1:3, 2 chlorines, 1:9:6 to 1. I mean, this is a routine MSc level. So by looking at nitrogen rule and isotopes, now you got more information, structure information. So nitrogen rule, what you got? Presence or absence of nitrogen, number of carbon numbers. Sorry, this carbon number of carbons. Types of fragment ions also you can get, whether neutral loss, whether radical loss. Isotopic pattern, number of carbons, type of halogens, number of sulfurs. So by looking together, you already have some structure information. So then next the fragmentation pattern. I think madam already, she said she covered, but she requested to,
Sir.
yeah.
You please go ahead, sir.
So
We
you
never
want me-
compete with you.
Yeah, so can I discuss this one, madam, or can I skip?
No, you please proceed. We
Yeah,
are ready to learn.
So in a fragmentation pattern, you are confined with only electron ionization. So most of the fragmentation books, everything written in electron ionization spectrum only. Don't apply everything to LCMS, whatever. Okay, those also fragmentation will be there, but those are, there is no electron in the LCMS spectrum. Whatever ion you got in the electron ionization, you got a radical. That's why fragmentation is too high and it is different. Okay, so most of the fragmentation is bond cleavages. Your molecular ion is cool only. That it will detected as a molecular ion. But some of the molecules, they express very high energy because of 70 electron volt. Then they break. Okay. So now you can ask a question: if molecular ion is detected, all the molecules are not fragmented. Why you got fragment ion? Okay. But thing is not like that. You are not sending one molecule. You are sending thousands of molecules at one stretch. So in that 1,000 molecules, few molecules are stable. They detect as a molecular ion, and few other molecules are unstable. They break, and they give fragment ion. Okay. The one which is giving fragment ion, it will not be registered as a molecular ion. The one which is registered as a molecular ion, it is not fragmented, it is went all the way there. So that is the one which you have to understand. Okay, so you have a direct cleavage, and fragmentation can be at double bond, fragmentation can be at lone pair of electrons, and so there is called Stevens rule, stabilization part of view. So this slide will give you a list of common fragments. Okay, if the fragment is 31, it is OCS3. Okay, there is no fragment 21, 22, 23, 24, 25. There is no fragment. If somebody says I have 25 last, put a namaskar. This is a wrong thing. Okay, so there are certain fragments you cannot expect. So first one is the homolytic cleavage. Okay, in homolytic cleavage, the sigma bond is broken. Usually the homolytic is alpha cleavage. People say that means this is the heteroatom, this is the alpha carbon. The alpha CC bond is homolytically cleaved. That means one electron came this side, the other electron is there on. In that case, you get radical and you get a nice stable ion. Okay. Then this is another alpha cleavage where the immediate carbon, this is heteroatom, this is alpha carbon and alpha cleavage. So here you get cation and anion. So like that, your any benzyl, madam was telling yesterday. So this alpha cleavage will give a tropylium cation. So in a CSIR, many times people ask a question. Okay, 91 what it could be, C7, S7. Okay, sometimes the benzyl the carbonyl here is 105 ion. Only these two will come in CSR exams. So this is homolytic cleavage. Okay, heterolytic cleavage means that two electrons are moved at one place only. Okay, like chlorine. Chlorine is a highly electronegative, so these two electrons are taken by it only. So leaving plus charge on the other end. So this is heterolytic cleavage. So all fragmentation patterns are either homolytic cleavage or heterolytic cleavage. That's all. Very simple. So other cleavage is so when it is cleaving, it will follow all organic chemistry rules. Okay, Stevenson rule. That means whatever after forming the fragment, whatever is stable, it will form. Okay. So how do you know which is stable? So you know from organic chemistry, primary carbocation is less stable than secondary carbocation and tertiary. Tertiary carbocation is more stable. Same thing apply here also. Okay. If it is fragmenting here, if it is tertiary, this will form high. If it is secondary, it will form low. Okay. So this rule is applied to all fragmentation patterns. Please remember it is equivalent to your organic chemistry stabilization, aromatic nature, okay, everything. Your alpha LL cation, 1,3 migration of resonance, everything applies here. Okay, it's all organic chemists. They love fragmentation patterns because they know which is stable, which is unstable. Okay. So this is a McLaughlin rearrangement. Now cleavage is gone. This is a rearrangement. Here gamma hydrogen is shifted to oxygen, and you get two parts, enol part and neutral olefin. But don't expect all the time charge here. Sometimes the charge can be on the olefin part also. If as per the Stevens rule, if this has a substituent which is stable, aromatic for example, then this will form. Sometimes both will form. Okay, that means in a given part, this will carry, the other part other will carry. So never ever expect only charge on the one part. I have seen in two parts, or I have seen in neutral olefin also. Okay, so this is important in structural reaction. So McLaughlin is a you know how it has formed. This is the name of the person, McLaughlin, and those who have not seen, you can see here. Okay, he is a McLaughlin. I met him in one of the meeting in US. So I thanked him because all my thesis work used McLaughlin rearrangements to detect chiral isomers, to detect many structural isomers. I use the McLaughlin rearrangement. It's very great, right? Other than McLaughlin, you have ortho effects where any aromatic compound, if two functional groups are in ortho position, they give a neutral molecule, whereas meta and para, they don't give this neutral molecule. Okay, ortho effects are very, very important in structural elucidation, and many times we use this one to eliminate meta and para position isomers. Okay, easily you can rule out possibility of meta and para isomers. Okay. So this is quickly I can give how alkenes and other functional groups they fragment. So if you see here alkane, very easy. All the fragments are separated 14 units. There's no question of if by looking at spectrum, every unit has a 2 units one homologous CH2 will be there, so you can detect easily. In the case of cycloalkene, it will form like C2H4 last. Don't confuse with retrodyl disorder. This is the saturated, there is no retrodyl disorder here. It only give this fragment. Whereas in alkene case, your alpha cleavage dominates here, and you get charge to the double bond, because charge to the next carbon, which is next to the double bond, is stable. Okay, allylic. That's why you get all these ions. In the case of cycloalkene, now your retrodyl disorder will come into picture. There should be one double bond, only one unsaturation in given cycle, and it will form back to diene and dienophile. Okay, and here also charge mostly in diene, but sometimes if they substituted, you can here also dienophile also you can have charge, and we have seen many examples where charge can be here or charge can be there. So you can have charge at both sides. Okay, this retrodyl disorder fragmentation has been used in many structural elucidation, natural products. This is norborine. Most of the norborine structures were elucidated by retrodyl disorder. Alpha pionine, beta pionine, many others. So you can find many examples of application of this fragmentation pattern in structural elucidation. Okay, aromatic very easy, like it doesn't fragment because aromatic compounds are highly stable. You get only molecular ion, only very few fragment ions. So again 91, as I already told you, topyl cation. Wherever benzyl is there, it will give 91. So when it comes to alcohols, you have alpha cleavage and you have water loss. If the hydrogen is next, it will lose a water loss, and if there is a double bond it forms. Very easy to identify, but if there is no hydrogen next to the carbon, it will not give you alcohol. For example, aromatic isomers, for example, phenol, orthoisomer, it will give alcohol, or sometimes metapara, it may not give. Like that, many other alcohols, nicely it will give fragmentation. Phenol, okay, phenol you can see OH radical, water loss, loss of water, in the ortho effects only you can see. Phenol will not give you a water loss. Okay? If ortho position, if some hydrogen is there, then only it will give a water loss. In this case, you can see there is a water loss 108 minus water 90. The beautiful thing in phenol, very structural elucidation, phenol will give carbonyl 28 loss. Normally people don't believe. There is no carbonyl group, how it is formed, how it has lost 28. But this is the mechanism how it formed. But because of this nature, most of the phenolic compounds were structural elucidation because of this carbonyl loss. Okay, very specific, and I use many times this phenol carbonyl loss for structural elucidation. Then ethers, very simple, alpha cleavage only, either this side or that side. You apply Stefan's rule, and whatever stable it will form. And aromatic ether, again, there is a rearrangement. If you have a gamma hydrogen, it will form is equivalent to your Claisen rearrangement, if you remember, organic chemistry people. And I did same Claisen rearrangement. I demonstrated in mass spectrometry also, using high resolution instrument, because this loses CO. CO cannot be possible if there is no phenol, unless it forms phenol after the rearrangement. So this I used in mass spectrometry, and orthoclazine rearrangement, sulfur Claisen rearrangement, nitrogen Claisen rearrangement, everything we have proved in mass spectrometry. So aldehyde ketones is straightforward, alpha cleavage, and if aromatic is there, you can get aromatic cleavage. Okay. Carboxylic acids easy, COH loss or formic acid loss. Ester is again, that ester can be anywhere, it can ether bond or carbonyl bond either side, it can fragment. So easy, very easy. Methyl ester 59, ethyl ester 70, 59 plus 14, 73. Like that, easily you can get ethyl ester, propyl ester information. Amides and amines, because of the nitrogen, it may not give this alkyl part. You only get because it's highly stable. The charge can be this side. So that's why amines will be problem to get structure at this side. Whereas aromatic amine, yes, because now the aromatic nature stabilized, so you have charge this side also. Other thing is aniline, like phenol. Aniline gives SCN loss, 27 loss. You can see 93 minus 27 is 65 here. It has CN radical and SCN both. So this is also another important fragmentation pattern. If you are analyzing aromatic amines, it can use this SCN loss. So I think it's already, it's repeated. The last one is the double bond equivalence. Okay, you got so much information with the mass spectrometer, and the mass spectrometer will give you the formula also. I told you, high resolution will give you the formula. So once you get the formula, you can easily calculate double bond equivalence. Is it not? Any organic chemist, they can calculate double bond equivalence. What is double bond equivalence? The number of double bonds, number of cycles in a given structure. So double bond will, this double bond equivalent will give you the structure information. How many double bonds there could be, how many cyclic nature there could be. For example, you got 91 peak. Okay, 91 peak means your double bond equivalence 4 already covered in the structure. Your double bond equivalence is 6 in the formula. 4 already covered. Now 2 you have to think about. 2 could be a carbonyl group. Okay, a cyclic nature, aliphatic cycle, something like that. So very easy to get double bond equivalent information. If you have, you can get structure. Okay, carbonyl 1, amide, you have amide 1 double bond equivalent, like that. Very important. But only thing is there is a small thing with the ions. Okay, if you are calculating double bond equivalent for the ion. Okay, so another point I have to tell you, even fragment ions with high resolution, you get molecular formula for the fragments also. Okay, so if you get a formula and if you know that it is an ion, that double bond equivalent calculation you have to be careful. So in this case, for example, you have a pyridine. Pyridine formula, if you calculate, double bond equivalent is 4, and even from the molecular ion you get 4 only. Okay, whereas with the benzyl cation, if it is considered equal, it will be 6, right? There are 4 here, 2 double bond equivalents in carbonyl charge. Okay, but because it is charged, what is charge means? There is 1 electron less. Because of 1 electron less, the double bond is not fully giving full information. That's why you get integer value 5.5, because it's a cation. Okay, so most of the cations, fragment cations, the double bond equivalence will be 0.5. So that you have to be careful when you are analyzing elemental composition information of fragment ions. Okay? So this is the actually tertiary information you get from double bond equivalence. Okay. So I think with this most of the interpretation part finishes. So maybe with another 2-3 slides, I will show you how we use mass spectrometry technique to analyze our degradation products or pharmaceuticals. Okay. So this is published already. Saxagliptin, highly saturated. There is no aromatic in nature. Very difficult to handle these molecules, right? So when you do, you know already, stability studies, we test the stability of the drug in acidic condition, basic condition, oxidation condition to understand the degradation of the drug and the toxicity of the degraded products. Because when you eat, for example, the drug by orally, if the drug is unstable, then acidic condition, because you know acidic in nature, then you get there is a possibility that these degradation products can form in our stomach. Then if those are toxic in nature, then you will be problematic to use as a oral drug. So like that, it's important to analyze the stability of the drugs at different conditions. So you have seen there are, I think, 6 to 7 degradation products were identified, and we have to develop HPLC method, and we have to get the molecular weight of each compound, and we have to get high resolution, possible elemental composition, and we'll go to isotopes, and we'll see how many number of carbon atoms possible in the given, like that. We'll do all basic thing. We apply nitrogen rule, whether it's the product has nitrogen or not. We see there are 3 nitrogens. Obviously, as 1 nitrogen, 2 nitrogen, it will give information. The degradation product has 1 nitrogen, 2 nitrogen. Usually, molecular weight will give you. Okay, so like that, we have to analyze such things. And finally, we are given structures of these molecules. Sometimes, for example, DP4 and DP5. Okay, so these are like isomeric compounds. If you see the chromatogram back, DP5 and 6, here down, oxidation, DP5 and DP6, both have same molecular weight. Okay, and we could identify one as the N-oxide. Other one is a cyanide with 2 nitrogen, and we are unable to tell where this oxygen could be. That's why we are given like this. But we know definitely the oxygen is here, and mostly it would be in this tertiary carbon or in this tertiary carbon. But to confirm it, we have to synthesize. But at least we know the oxygen is there. Like that, this also DP2 and 3 also very critical to characterize, and we have used mass spectrometry technique for substitution. So it takes not a 1-day job or 2-day job. Okay, so it will at least 1 year job to establish HPLC method, to do the MSMS. Sometimes we isolate the molecule and compare the fragmentation, what isolated, what synthesized. Sometimes we also synthesize and compare. So synthetic means again it will take another 1 year to synthesis, to purify the synthetic product. And so those who want, you can see this published in 2014, analytical methods. The other one is, this is a natural product we have done. Everybody who is working in natural product, they know. So andrographis granulosa, right? It's mostly available in Tirupati. So we also contributed a new species of this one. When you took direct mass spectrum, there are 2 ions have come, 283, 285. So we got elemental. So usually what do you think by looking at the spectrum, it is M+2 and 33%, right? You think it is a chlorinated compound with isotopic pattern. But our high resolution did not give presence of chlorine. Okay. Then we thought these two are two different molecules rather than ascopic pattern. Then when we did LCMS, these two compounds were nicely separated, 285, 283. Okay, so direct analysis will mislead here. We think isotopic. Okay, so nicely 283 and 285 are separated, and we have done MSMS of 283, 285. You can see here heterodyl rearrangement helped us to get these two structures. Okay, so you can see this is if the double bond is here, it is a cyclohexene. So it will give nicely. One second. Hello, I'm in webinar body. I will call you. No, I'm live. So this RDA, retro disorder, you can see these fragments were different, right? One is 165, 119. So here, because it has double bond, it is 117 and 165. Okay. So this helped us in getting this structure. The difference is only presence of a double bond. Okay. So it is reported in 2017. For details, you can see that. Another thing is, these are alcohol compounds. We have used negative ion, not positive ion. Positive ion will not come, will not ionize this molecule. So I think I stop here. So I started with mass spectrometry basics, and I touched upon the terminology. Then I explained you the main parts of the mass spectrometer. Then I briefed you what are the classical sources and what are the developments in mass spectrometry, and analyzers, what are the classical analyzers, and what are the high resolution analyzers and detectors, and like a personalized pixel, how you can get your own mass spectrometer, planning yourself, choosing one source, one analyzer, one detector. So then I moved to the high resolution part, MSMS part, then structural exploration using elemental composition, high resolution, and fragmentation patterns, homolytic cleavage, heterolytic cleavage, rearrangements, and its use. Sorry, one second. Hello. Madam, I am in a live webinar. Can you call me after 40 minutes? Yeah. Sorry, since I am in the office, I have to attend the question. So then I explain you fragmentation pattern in different classes of compounds, and but make sure that is only for EI. When it comes to electrospray, ionization, and fragmentation, it will be different. Mostly you get neutral molecules, which I explain you with known molecules. Some of the our own examples. So thanks for your patience, and stay at home, stay safe. And now it is open for questions.
Thank you, sir. Thank you for your amazing lecture, sir. It's really impressive the way you have explained by giving various examples with colorful images. It's really, we enjoyed a lot, and the efforts you have made to prepare, to present a colorful PowerPoint presentation to the participants is simply superb, sir. Thank you for your wonderful.
First of all, before you continue, so my thanks to you also, because as a convener, I got this opportunity to meet the people, go to the, I don't know how many people attended this one. Any number, madam?
Yeah, 250 members are online, sir. The rest of them are watching live YouTube.
Okay, okay.
So now the questionnaire session, sir, with your permission, I request Dr. P. Rajkumar, Professor, Department of Pharmaceutical Analysis, will proceed for the questionnaire session.
Thank you, madam. Am I audible?
Yes.
Yes, sir.
Sir, very good morning, Dr. Prabhakar, sir.
Very good afternoon, sir.
I'm Dr. Rajkumar Kudari. We have few questions from the participants, and first of all, I would like to invite the participants, if they have questions, directly to ask you. Any of the participants who are interested to ask any questions, you are welcome. You can raise your hand so that we can unmute you. I've noted some few questions from their chatting, sir. First of all, I should congratulate you that is that you, sir, standing beside McLafferty?
Yeah.
That is very nice of you, sir. A renowned personality. You're getting.
Not only McLafferty, the Fen and Tanaka, those two noble laureates. I met them in US, and also they personally came to our center.
Oh, fine, sir.
It's fortunate to have them here.
It would be better that if we from the teaching fraternity know such legendary personalities visit places like yours, because yours is a research center, and even we can show some light, we can throw some light about them also. And if at all, if we find such an opportunity, we can at least have a hello with them. And moreover, regarding, we find a thin line between this teaching procedures and your research procedures actually. And we as teachers, we wish you, sir, your contribution. We require your contribution. We invite your contribution towards our research projects, because some of our students, they'll be working on LCMS for right now for this year. Some of our students are working on impurities, metallic impurities in pharma compounds, and we are proceeding for ICP, inductively coupled mass spectroscopy. And we have a doubt regarding it, whether it is good to go for mass ICP or atomic absorption spectroscopy to identify the elemental impurities in the pharmaceutical APIs, actually bulk materials.
So actually we had ICP-MS 20 years back, and few years ago we just condemned the instrument, and we are procuring new equipment. However, we also have ICP OES instead of mass spectrometer. You can have a OES detector. So that is definitely working now, and we are in the process of procuring a new ICP-MS. So, as to understand your question, yes, it is important to analyze your metallic impurities in APIs, and we have a enabled testing facility here to analyze metal ions in API. So you can see in our enabled certificate also. So only thing is you can use ICP-AA, I mean AAS, or ICP-OES, or ICP-MS. Okay? MS is always better because it will cover more number of metal ions.
Yes, sir.
And also easy to deal with any kind of acidic compounds, any kind of samples you can digest with latest technology. And other thing is it can also cover you the speciation. Sometimes you should know the what exactly the iron 3 or iron 5, like that. Speciation also sometimes important. That will give you the ICP-MS would be better, but ICP-OES is equally important. It can cover PPP level or PPT level sometimes. So I advise you, you can approach us. We are ready to accept samples in API. We'll help you.
Thank you, sir. Thank you. Some of our students were going through such projects, and One more question from one of the participants. It is about barium sulfate. Whether being barium sulfate is a radio opaque, whether it is possible to identify the impurities or degradation products from barium sulfate palatable liquid, which is being used in radiology here in medicine.
Yeah, I think this atomic element level ion, inorganic ion, normally we don't deal. Okay, so we normally confine to organic chemistry, organic molecule. So to answer your question, it may be possible, but I am not a guy to look at the degradations of inorganic components. Okay,
Yes, sir.
so I can convey this one to my colleague.
Sure.
So we have who is working on ICP may do, but I will note it down and definitely answer it, get back to you.
Thank you. Nice of you, sir. And one more question: whether we can estimate complex mixtures or isolate them, isolate some of the active constituents from complex mixtures. Maybe perhaps this is from herbal constituents, I suppose.
Okay, so yeah, as you said correctly, my next question will be like that. So is it the complex is organic complexes?
Yes.
Organic complex is possible to separate by HPLC and easy to ionize by mass spectrometry because it is already ionized. The metal complex means the metal ion is already ionized. You don't have to struggle to ionize the complex again. So it is a pre-ionized molecule, easy to analyze, and
Pre-ionized status.
we
Okay.
have published many metal complexes analysis. And the beauty of this mass spectrometry is it will give you coordination number of the metal ion. For example, your ligand is like 1:1 or 1:2. Based on the mass value you get, you nicely it comes the information. Other thing is it will also give you the oxidation state of complex. So iron could be +2, iron could be +3. It can be any metal ion. Okay. What I'm saying is not only metal complex analysis, it will give you beyond that. It will give a ratio, it will give oxidation state, and also it will give you it is a coordination bond or a ionic complex.
Nowadays, in pharmacy, the purview, the viewing the purity of the pharmaceutical products has changed. Previously, we used to calculate, we used to count on assay, finding the percentage purity of a drug. But now, as it goes, even every drug is 99.99 pure, and this ICH guidelines and all the authorities, apex bodies were asking about what is the impurity, 0.01% impurity, and they are asking us to profile the impurity so that we should characterize the impurity, we should isolate it, and we should give a data regarding what are the impurities present in particular drug. When it comes to manufacturing of tons together, it amounts much, sir, around 2 to 3 kgs of impurities comprise. So in such case, you were discussing about saxagliptin, uh, about degradation products. These degradation products we expect during manufacturing, taking a bulk drug and making it into formulation. Then we come across this degradation products like worn out metal ions. And how do you refer about certain degradation products in many of these pharmaceutical preparations? Because nowadays every apex body is serious about this degradation products. Can you throw some light, sir?
Madam, actually there are two things mixing here. One is the impurities. The
Yes, sir.
impurity may not be coming from degradation of main product.
Yes, yes. Impurities is right from bulk.
The impurity, as you said, 0.01 is exactly now because US people say we are paying to your drug, not for your impurity.
Impurity.
That's why that
Yes,
ICS
yes.
guidelines were made, and many people come to ISCT for the impurity profiling. So impurity profiling, not only this one, it will also help you in process improvement. Okay.
Yes, process impurities.
That
What we call them as degradations.
yeah, because if one person is following one particular process the impurities present there may be different from other process. So this also there. So it is required, and mass spectrometry definitely helps in this one. But degradation, as I said, degradation of the main drug is different. So that is you expect main drug is in pure form, but after subjecting to the
Sir, Prabhakar sir, we are unable to hear. Sir, it's not audible.
నువ్వు అడుగుతావా
Prabhakar sir,
సార్? హలో,
that's interruption. Sir,
yeah, am I audible?
Yeah.
now it's audible, sir.
Yeah, okay. So it is resetting again. Okay. So it is possible, sir. Yes. So actually, not only pharmaceutical, now the demand is coming for agrochemicals also. Okay. The agrochemicals also used in field, and it is coming to the food, and it's coming back to you only.
Yes.
So actually, we already
Characterization of
started,
impurity.
working on it, and we are already publishing also. Okay.
Nice.
So impurities not only in pharma, agro also there.
And one more question from one of the participants: how to analyze enantiomers by mass spectroscopy?
Yes, enantiomers. First of all, are you separating the enantiomers? Chromatography is important. Okay.
Yes, sir. Isolation.
Yeah, yeah. So if you separate by chromatography by using chiral columns, there is mass spectrometry. There is no problem, right? Because
Industrially, they usually do it depending on the boiling point and melting point.
Yeah, yeah. But if you have two together and directly recording mass spectrum, may be difficult. The mass spectrometer cannot separate in the analyzer or this one. Okay.
Yes, sir.
But certain diastereomers can be characterized because they have different structures. Okay, so many times my many publications are there. Their fragmentation pattern may be different for the diastereomers, not for enantiomers. Okay, but we used in mass spectrometry chiral molecules. We make a complex of chiral molecule in the source itself, mass spectrometry source. Then form a diastereomer. That diastereomer, when it's breaking, it will be different. So that way we have done about 15 to 20 publications on that. It is possible.
Well, the chirality might be different, but the molecular status is same, no, sir, for both the enantiomers.
Yeah,
And if it is a mixture of, if it is a racemic mixture also.
Yes, we need chiral reagent to make diastereomer. Then it is possible by mass spectrometry.
That's very fine of you, sir. And once again, congratulations for having close access with one of the legendary people in the spectral analysis. And now over to Madam.
thank you, Dr. Rajkumar Garu. Sir, Professor Rajita Madam is waiting to interact with you. I request our technical team, please unmute Professor Rajita Garu, Padmavati Mahila University. Rajita Madam.
Madam, just a minute. Battery is running low. I will put my charger.
No problem, Madam. Yeah. So nice to seeing you, Madam, today in this session.
Thank you.
Though you have a vast experience, Madam is continuously keenly observing from the starting the session to end of the session, Madam. Thank you for your patient listening. Please go ahead, Madam.
Yes.
Our sir is waiting.
Am I audible?
Yeah, it's clear.
Yes. Good afternoon, everyone. Good afternoon, sir. This is Professor Rajita from Padmavati Mahila Vishwavidyalaya, Tirupati.
Welcome, madam.
Welcome, madam.
Yes, sir. Thank you very much, sir, for your outstanding, elaborative, and enlightening lecture on recent advances in mass spectrometry. I hope all the students, including me, gained knowledge as the sir touched from fundamental principles to recent advances on MALDI imaging hyphenated techniques such as LCMS, MSMS, etc. Dark techniques also. It is very interesting one knife intelligence knife you told sir about the cancer. It is very much interesting. And you have covered all the fragmentation pattern rules and everything. You explained very well and we understood everything. And you made the subject, interesting by your attractive and lucid slides. I'm in a hurry because it may go off. That's why I'm talking very fast. Okay. And finally, I thank Sunita Madam, convener of FDP, and her team for their meticulous efforts in arranging sessions with resourceful resource persons, in collecting feedback from delegates, and in framing wise questions in Google Forms. They are very tough to answer, and we have to refer even. I referred for some questions from Google. And okay, sir, thank you very much, sir. Thank you. And hope I may contact you, and I will call for our your lecture in our college also. Please, I welcome for my college also. Please accept our invitation, sir.
Already accepted, ma'am.
This
So,
Okay, it's okay. It's pleasure. Anytime.
Yes, you have explained very well with a cool voice. Very well. Thank you. Thank you very much, sir.
Basically, I am a Telugu medium guy.
Yeah, I can see you are from Nalgonda. You are from Telangana. Myself is also from Telangana.
What I want to emphasize is, till my BSc, I am in Pakka Telugu. So after joining the Usman University campus, I had to use my English.
Yes.
So hope my English is okay.
Yeah, excellent. Excellent, sir. It is very happy to associate with you. Sunita madam, thanks a lot that we have learned today a lot.
thank you so much, madam. So I think you have completed my duty, covered closing remarks. Now I request our technical team to connect Dr. Gaumati from JSS Booty. I request our participants, if anybody wants to interact to the speaker eminent personality, please you please inform to us immediately. We will unmute. Madam, welcome, Gaumati.
Good afternoon, ma'am. Good afternoon, sir.
Yeah.
Really, it's very happy to share my views. Really, it's a wonderful session. I'm attending 2-3 days. Organizers are working very well. You are the very good organizers. I never ever seen, because every day I'm getting properly feedback, everything. This session is so good because for everyone we are doing the isolation, but some cases we don't know how to interpretation, how to do the interpretation with mass spectroscopy and all. So it's very useful for students, both the teachers, even teachers also don't know how to do the interpretation properly.
Yeah.
So it's very useful session. Thank you so much, sir.
Yeah, thank you.
Thank you so much, sir. And thank you so much, Madam Sunita, ma'am. Thank you,
Thank you. Welcome, madam.
Okay.
Always we need your feedback.
Okay, thank you, ma'am. It's my pleasure. Thank you.
Welcome. Yeah, with this end, I would like to give the closing remarks. Today's speaker, Dr. S. Prabhakar Garu, has focused on certain points which we have never heard before, especially on laser orbiting spectroscopy, ESI, Stevenson's rule. So many things we have learned from today's session, sir. Imaging mass spectroscopy. And sir has given a clear picture on how to choose a positive ion mode or negative ion mode, detection of ions, interpretation of spectra, and covered about the new advancements and techniques in the instrumentation field, which has made a significant changeover in the field of research. To become a good scientist, one has to unleash the potential of the lab instruments and has to work on it. We have learned so many things, sir. There is a lot of scope to do research on mass spectroscopy with the participation of outstanding experts. We hope productive discussions would stimulate new creative ideas to translate new discoveries into better practice and application. We appreciate you being here. Thank you, one and all. Tomorrow we are going to end the session. Tomorrow, Professor Leelavati Garu from Osmania University is going to address us about the overall structural elucidation, interpretation by seeing all the spectra. So, waiting for you until tomorrow. Thank you, sir. I profusely thank a well-renowned speaker of today's session, Dr. Prabhakar Garu, Senior Principal Scientist, IICT, for his outstanding lecture. Thank you for accepting our invitation, sir. Thank you for spending your valuable time with us and the efforts you made for preparing a wonderful PPT, sir. Thank you. I thank you one and all.
Thank you, madam. We are hereby ending the meeting. Sir, anything to say, sir? Prabhakar, sir?
Nothing else. So I can leave now? Yeah.
Yes, sir. Hereby we are ending the meeting.
Yeah, a recorded version of this program is available in our YouTube channel. We also like to hear from you. Thanks. Thanks again for joining us today, and we will see you tomorrow. Thank you.